In this tutorial, we will cover the different physical states that impurities can be present in water. Substances can exist in water in one of three ways. When a substance is dissolved, there is only one physical phase present, the liquid phase. The substance can only be removed by accomplishing a phase change. This can be done through distillation, precipitation, adsorption, or liquid extraction. As we discuss treatment processes throughout the semester, we will see that precipitation is very common, as is adsorption. Precipitation is one of the key processes in water treatment to remove dissolved substances, and adsorption is one of the key processes used in air treatment or air pollution control. You may have learned about distillation and liquid extraction in other courses. These are not very common in environmental engineering because we deal with such mass volumes of water. Distillation, you'll recall, is simply where you heat water to vaporize the pure water fraction, and you're left with a solution that contains condensed pollution because the solids would not evaporate. The clean water, or pure water vapor, could then be condensed, and the distillate would be clean water, and the pollution would remain in the condensed solution. In precipitation, start with one phase that has the pollution involved. You add a chemical, or you change the temperature. You shift the equilibrium such that the pollution precipitates out, and so you are left with a supernatant, which in water treatment is what would be taken to the distribution system. So we will see precipitation reactions occur on a mass scale in the water treatment plant. Adsorption, this is an image of activated charcoal. It could also be activated carbon. And what you see here is gas molecules that would adsorb to the surface of that particle. The second physical state we'll discuss is suspended solids. In a suspended situation, you have two phases that are present but are completely mixed. You have a liquid and a solid phase. These can be completely mixed. When the solids are large enough to be removed by physical methods, we can apply sedimentation, filtration, and centrifugation. Sedimentation is simply when particles coming in that are suspended are large enough that they will settle by gravity. So in this situation, you allow gravity to work upon the particle size that has some density and a diameter, and if you apply Stokes' law, you can predict the settling velocity of a particle in this situation. This unit here is referred to as a clarifier or a sedimentation tank. Now, in environmental engineering, a suspended particle is defined explicitly as anything that can be filtered out by a glass fiber filter. And this is what a glass fiber filter looks like under a microscope. You'll see that it is just a collection of glass fibers. There is no exact particle size that settles on this, but there is a nominal pore size, which means an average pore size created by those filters that may vary, but typically is around 2 micrometers. So in environmental engineering, to do a suspended solids test, we create a filtration unit, we put a glass fiber filter on top of it, and we pour water through and we vacuum filter. We weigh what remains on the filter. The method of suspended solids is defined in a book referred to as Standard Methods. It is produced by the American Water Works Association, the American Public Health Association, and the Water Environment Federation. So just to summarize, suspended solids are physically defined as when a solid is suspended in a liquid phase. In environmental engineering, we have an explicit definition which is defined in the laboratory through filtration of glass fiber filters. From a treatment perspective, to remove suspended impurities, we will see that sedimentation is extremely prevalent because it uses only gravity, and gravity is free and very cheap to implement if you have the space allowable. Sedimentation is one of the key process units used to remove suspended particles. We will also see filtration involved, especially in water treatment for sand filters. Centrifugation is not as common because, again, we deal with mass volumes of water, million gallons per day, and the energy cost to centrifuge that much volume would be extreme. The third physical state that impurities are present is colloidal. Colloidal particles are in the size range between dissolved and suspended. These are extremely stable suspensions. You will know of a colloidal system as salad dressing or mayonnaise. So it is extremely difficult to remove colloidal particles. It can be energy intensive. The options available to us are high force centrifugation. And when you see high force, you should think energy intensive. This is not applicable for a million gallons per day because of the energy cost. We may also filter through very small pore spaces. This is also energy intensive due to the head loss that must be overcome. Colloidal substances are often measured as turbidity. And so we will often refer to the turbidity of a water. And turbidity is simply a laboratory technique whereby light is shined through a solution and the reflection of this light is measured. It is given units of normal turbidity unit, NTU, and so the higher the NTU, the higher the turbidity. There are three physical states in which impurities are typically present: dissolved, suspended, and colloidal. For dissolved substances, we typically use precipitation and adsorption to change the physical state of the impurity and remove it. In precipitation, we change the physical state from an aqueous state to a solid state, and we remove that. In adsorption, we also remove the substance, usually from a gas state or an aqueous state, to a solid state by adsorbing it to the solid. In suspended solid situations, we settle the solid, again, removing it from the aqueous phase to the solid phase, or we filter the solid, removing it from a dilute aqueous phase, either to a concentrated aqueous phase or a brine, or to a solid phase. Colloidal particles are extremely difficult to remove, and so you'll see here that I haven't highlighted any of these options as common. In reality, what we'll see is that we try to change the colloidal state to a suspended state and remove it either through sedimentation or filtration. And we'll return to that in water treatment. I want to take a few minutes to cover dissolved gases. Henry's law is defined as the partial pressure of a gas in the gas phase, Pi, equals the Henry's constant, which is specific for a gas. And so this is something that you would look up in a table for each gas. And that is multiplied by the aqueous concentration. And so we can also write this in terms of the percent, the molar percent volume that a gas is present in air. And that would be a function of the total atmospheric pressure, PT. And so this is a table from your textbook of common Henry's law constants that we will work with. All of these constituents are common in air, and you'll see that the Henry's law constant can be written with two different units. And so this one is in terms of moles, and this one is in terms of milligrams. And you can pick either of these Henry's law constants that are convenient for unit conversions. The typical composition of dry air at 1 atmosphere is 78% nitrogen, 21% oxygen, and just 0.03% carbon dioxide. So you can use Henry's law to solve for the aqueous concentration of a gas. And so this is something that you would consider as a solubility constant. And so I want to introduce this because dissolved gases do become a constituent of water. And so in this example, we're asked to find the solubility of oxygen in milligrams per liter in pure water at 1 atmosphere and 25 degrees Celsius. These are significant because Henry's law constants are explicit for temperature and pressure. So, using this form of the equation and looking at the previous table, the percent volume of oxygen, P, is 21%. So 21% by volume is what we will use in the form of the equation. We are trying to find the solubility of water, so we can rewrite this equation as Ci aqueous equals the percent volume times the total atmospheric pressure divided by the Henry's law constant. From the table, we can assume that the partial pressure of oxygen P is 21% by volume. It's given that the total atmospheric pressure is 1 atm, and now we have to find the Henry's law constant. Because we're asked to find the solubility in terms of milligrams per liter, when I go to the table, I will use the form of Henry's law that's already in terms of the milligram of the gas. So for oxygen, the Henry's law constant I will use is 2.40 times 10 to the negative 2. 2.40 times 10 to the negative 2 liters times atmosphere divided by milligrams. So substituting these into the equation, I see 0.21 times 1 atm divided by 2.40 times 10 to the negative 2 liters atmosphere divided by milligram. The atmosphere cancel out, and this is equal to 8.75 milligrams per liter. Now, if we step back and think about what this example is showing us, at equilibrium, when the atmosphere is in contact with water, at 25 degrees Celsius and 1 atmosphere pressure, we can expect the dissolved oxygen, the saturated dissolved oxygen, to equal 8.75 milligrams per liter. Now, you can look up the solubility constant of dissolved oxygen in the back of your book in the appendices, and you will use that because this is a function of temperature and pressure.